Hello, 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 and welcome to this reactor session on an introduction to Orleans. Look forward to talking to you about Orleans, what I think is one of the most innovative and exciting projects to have come out of Microsoft research. And I know Ben and I are very keen to talk about it and the experimental work we've done with it. So before we explore that, let's just do a quick introduction. So, hi, my name is David Gristwood, and I'm a cloud solution architect, and I work for Microsoft.
Hi, everybody. My name is Ben Coleman. I'm also a cloud solution architect, work for Microsoft in the same team as David. Spent a lot of time working with David on this particular project and exploring some of the sort of techniques around microservices in Orleans.
So cool. So let's get going and explore this. So this is a session of 4 parts. Ben and I are going to alternate between the two. So I'll start by talking about Orleans, give a little bit of a background to it because there's a lot to cover conceptually. Then Ben will take over and talk about Smilr, a microservices showcase that he's been working on for quite a while now. We'll then switch tack slightly, and then I'll explore how we took those ideas of Orleans and plugged them into Smilr and built part of the service using Orleans. And then finally, Ben will talk about how he took that implementation and deployed it into Kubernetes. So that's the journey we're going to go on over the next sort of 50 minutes or so. So let's start with an introduction to Orleans, and because I'm going to guess, based on my experiences, not a lot of people are aware of this project and the background to it. It's very interesting, very exciting, very innovative. So we want to kind of set expectations about, we don't assume knowledge of this to get up and going. We can't talk about Orleans without talking about the actor model. This is what it's all based on. Now, the actor model is a programming model. Got to say this up front. And like any programming model, such as CQRS or Lambda or something like that, you have to very much buy in to the programming model. All these models tend to be suitable for certain types of architectures and not for another. So picking the right kind of architecture is critical to success. For example, Ben and I've worked on CQRS projects. It introduces a layer of complexity, but the idea is in complex systems, the benefits it brings outweigh the potential complexity. In the case of the actor model, it was something that was designed to address some of the issues concerned with trying to build and run highly distributed, highly performant concurrent systems. Now, interestingly, it has its roots in a paper that was showcased in 1973 that actually was more influenced by hardware. The original idea was to imagine thousands or tens of thousands of little microprocessors, each with their own memory and a bus gluing them together, sending messages between them. And the idea was that if we adopted this sort of model, we could really scale out big time. And indeed, there have been several attempts at this. If anyone's been around the industry a while, they may be aware of the NMOS transputer. And I used to program in Occam, parallel programming language, all trying to address this idea is how do you build a system that can scale out using messages. In its early years, I think it's fair to say that the actor model sort of languished a bit and just remained more an academic discussion of how you might build such systems. But with the cloud, the lowering cost of processing and memory, there's been a desire to sort of revisit that. I think there's been a lot of interest more recently in it. Originally, Ericsson picked it up for Erlang, but that was more an internal project. Few people may have come across Akka as a name associated with actors, but they're all trying to take the same thing of this concept of actors and make them real. And in the actor model, the idea is every actor has its own state and it communicates with the outside world via asynchronous messages. So messages flow across the system and these actors receive the messages and based on their own internal logic and local state, make decisions. Perhaps a sensor sends in data and the internal state needs to be updated. Or perhaps as a result of something happening, more actors need to be communicated with, and the message needs to spread out. And this is the model it was academically exploring. And its goals, though, were to reduce complexity in complex systems, because the sorts of systems that actors are really envisioned for were those big complex systems that are hard to write and hard to scale well. So by building an environment that avoids deadlocks, avoids the issues around re-entrancy, implements asynchronous communication, we can have systems that scale to thousands or tens of thousands of actors and make them perform well. It's also received a lot of interest for performance in terms of, and this is what we will be discussing today, instead of the middle tier in an app being used simply to wrap around CRUD type calls to a backend database, let's actually implement some of that logic inside the actor. So Orleans is an implementation of this model. It is both a programming model, as in there's an API and an implementation, which we'll see for real here. And there's also a runtime, as in an environment for these actors to exist. And the two together are the winning combination. That's what really, I think, makes it a very attractive, nice, clean programming model, excellent performance implementation. It came out of Microsoft research. It's open source, and now started with the normal traditional .NET, now it's .NET Core, and that's really where it's come into its own, given its ability to run on Linux, Windows, and Mac OS. It makes no prescriptions about where it can run. You can run it, as they say, on bare metal, you can run it in VMs, you can run it on premise, you can run it up in the cloud, and more recently, a lot of interest in running it in Kubernetes, which is what Ben will explore towards the end of this session. Initially, its usage was mainly inside Microsoft, and I'll come back and revisit and talk a little bit about Halo, but it's also being used by a lot of big name companies, a lot of interest for these high performance systems. In Orleans terminology, a grain is an actor, so we'll tend to use the terms interchangeably, and it is indeed the building block for all the logic here. On the right hand side, if you've got an interest in this paper is really interesting. I've read it many times, and I said in 2014, I worked with a team in 2015 when we were running an early adopter program, and it's a very academic, rigorous paper that describes the whole background to this. This session, we're going to pick elements of that and explore them from a programmatic viewpoint. One of the key things that's interesting about how the team took the actor model and implemented it was the idea that grains always exist. They're virtual. You don't need to think about their creation and their destruction. They're just there for you whenever you need them. And that simplifies the programming model, but it does have some interesting side effects potentially that you need to be aware of. And in line with the goal of actors, internal state, send and receive messages, and they only come to life when a message comes in. And they have some more advanced features like timers and a sub-pub model, which makes it easier to get notifications when things happen in the outside world that can then trigger actions. I said it was a programming model, so one of the obvious questions is, when would you use this? Well, at one end of the scale, we wouldn't be building an accounting package in this. I wouldn't be building a database system. What I found is that when you have a model of something that is autonomous, independent, with its own behaviors and the like, Orleans is a potentially really good fit. So, for example, IoT devices, they are great. You can imagine a world in which there is a one-to-one mapping between an IoT device generating data and a grain inside Orleans that's receiving that data and holding it locally, and based on the data coming in is potentially making decisions. So, for example, a temperature IoT device that's sending temperature information in, it may be that if a temperature exceeds a certain threshold for a certain period of time, the grain then initiates some action by calling another grain that may raise an alarm or kick into a cooling system, for example. In Halo, on the right-hand side, you'll see from that paper an example of how it was used in the present system. So if you're a Halo 4 fan, you may remember Waypoint, the app that lets you see what was happening in the game and what your standing was. If you joined a game, say you're red versus blue, 32 players, what would happen is a grain would be created that represented the game and a grain for every player. And as updates were received from the game in real time via this heartbeat call, they would be cracked open, routed to the right actor, and then the information would be disseminated to each player, and then that would be reflected in the web UI. So if someone left, someone joined, headshot kill, for example, all that would be handled inside the grain. So it's a great model because each game has a degree of autonomy, but brings together a certain behavior. In terms of working with these grains, well, it's a great pun, but their grains live in silos, and that's the runtime aspect of what the Microsoft research team brought in building this. So you can see in the diagram a number of grains that live in 3 different silos, and Orleans hides the complexities of the placement of these grains. So when you make a call from one grain to another, if it's in the same process address space, it will be automatically handled. It has to be serialized and deserialized and moved across the network. That's all done for you transparently. So it manages that, it garbage collectors away the grains when they haven't been used for a while. It continually monitors the health of the system. So if there's a failure, it will take action to reinitiate that. So we'll be exploring that. We also see on this diagram there tends to be a wrapper that protects the grains from the outside world. So we use the terminology of a client. That's the only thing that's allowed to make calls into the silo, and typically we wrap that behind, say, a web API. You'd never typically expose that onto the internet. So in our model we'll talk about, say, an MVC web API, taking calls from the outside world, validating them, transforming them, and then making client calls into the silo system. From a programming viewpoint, it's helpful to perhaps think of a grain as a combination of an identity, which is its key, because every grain must have a unique key, the behavior, which is an interface that describes the methods and the methods themselves, and potentially state that may need to be saved at certain critical points in order to ensure the correct behavior of the system. So it's a nice little way of thinking about the design of a grain. Because everything is message based, everything is rooted around interfaces. So you define your interface as your starting point, derive it from one of the Orleans defined ones that indicates what key will be used to address this. So here, iGrain with string key, I'm saying that a string is going to be used as a key for this, and then I define my methods. Everything has to have a task in front of it. I think when I first started playing with this, that was the thing that took a while to get my mind around, that everything has to be asynchronous, everything has a task, whether it's just a simple result or a list of something. That's enforced to make sure that everything is asynchronous. Inside the grain, this is the world's simplest. This is the moral equivalent of a hello world type grain. We basically have the ability to send a message and retrieve a list of the internal messages. So the things of note here are the fact that at the top there, we have a store for the internal messages. So every time a message arrives, it's added to that private list. And then we have a write state async method that's used to persist that state. So we have a checkpoint. So if the grain needs to be garbage collected away, or there's a failure on the underlying hardware, we've got a checkpoint that we can recover from. And from the client's viewpoint, remember the client is in this case the web API. It reaches into the silo with this get grain call, passes the key of the grain. So you've got here David GRI and Ruben here. And once I have a handle to grain, what I will then do is make asynchronous calls into it, and the underlying infrastructure will handle all the hard work, the heavy lifting of routing that request to the appropriate grain, bringing it to life if needs be, letting it process and return anything. And this is the constant cycle here that we find with grains. Finally, for this bit, I've mentioned a couple of times about state and managing that. There are some scenarios where you perhaps don't need to persist the state. So if something would happen to the grain, the state's ephemeral, we don't need to worry about it. But a lot of cases you do care about the internal state, and making sure that that's resilient and robust is part of the programming design. So on the left-hand side, you'll see the diagram that talks about the way in which grains come to life. So the life cycle is when you reference a grain, if we've never seen one before, it's never existed before, because these things are virtual and always exist, we will automatically create it for you, bring it to life, initialize it, and then it's ready to receive your calls. At the other end of the scale, if a grain's been hanging around for a while and hasn't been used, what we want to do for performance is free it up to get the thread and the memory back, so we persist that grain to disk, and that all happens silently in the background, so that you can view an estate of millions of virtual grains, interact with them without thinking about that life cycle. But in the background, we are managing that to help you create these really big scalable systems. And the mechanism, and we'll see it in action when we talk about the implementation of the Orleans version of Smilr, is that you define an interface that contains all the member variables that need to be persisted, and then plug in a storage provider. And there's a load provided by default with Orleans, and a community that's involved in building more. And again, this is the nice part of the ecosystem, that people are choosing whatever stores they want to persist that stuff. We use table in our example because it's nice and easy and simple to track. Right, this is the point where I hand over to Ben.
Hi everyone. So I'm just going to share my screen here. Getting some echo, I think. David, do you need to go on mute? That's better. Thank you. Sorry about that. So yeah, I'm going to talk a little bit about this project called Smilr that myself and David worked on. It's a microservices application, a sort of kind of showcase, a reference application that we've created. And then this isn't necessarily about Orleans per se, but then we'll bring it back together at the end and explain about how we brought Orleans into this project. So some of the goals of this project and how it kind of came about, the kind of genesis of it was myself and David were doing a lot of presentations and talks to Microsoft customers around Azure technologies, compute patterns, design, and architecture considerations for moving to the cloud.
Then we seem to have a sharing issue with the slides. Sorry.
Okay. I'm definitely sharing. Sorry about that. Is that better? Just nod if you can see them. Yeah. Okay. Sorry about that. Teams technology snafu. So the way this came about was trying to come up with a system that helped people understand the different architectural choices that they would have, try and showcase some of the Azure capabilities, because we wanted people to be able to adopt Azure and have an application that showcased different approaches and provided a kind of end-to-end scenario for people to explore the different patterns, a key one of them being the microservices pattern. Alongside this, we wanted to develop a real application, a simple hello world or some sort of theoretical code on a slide. We wanted a real application we could go and learn ourselves and help our customers learn, and also explore the kind of modern way of developing applications, the sort of modern patterns and technologies to be able to do that. So what we came up with, kind of concept, was this idea of a sort of sentiment capture application. This is the kind of classic thing you see at sort of airports and various places where there's five or six faces, and you press one of them to say how happy you are with the service you've had that day. We would create like a digital version of that we could use actually in our events and workshops and hacks to gauge sentiment. So to create a system for that, we had a concept of using a kind of microservices pattern where we'd have multiple, loosely coupled components. At this stage, there was no implementation. It was just kind of conceptual. So we knew obviously we need somewhere to store data. Would we use a relational database? What would we use to store data? We'd obviously need some way to access that data, some sort of API in front of that. And obviously we need a client. We need people to actually use this. It needs to be usable by end users. So there's going to be some sort of web application. Wanted to explore the use of using single page applications. It's a kind of JavaScript approach where a lot of the logic is moved across to the client side. And then there needs to be a data access layer for that to be able to be used. So at this point, it was still kind of fairly conceptual. We knew we needed to use sort of standard patterns like REST and see how we would implement these different services and how many of them we would actually need at this stage. So really the way this all took shape, the core of it became the API. So what got designed first was a kind of mock version of the API. And from that, everything got built out. So from the API itself, there's a sort of specification of what data we needed, what the entities looked like, and what the operations would be on top of those entities. With that API in place, you could start to wireframe and sketch out the front end part, which was the single page application in this case, and also start to scratch out, a working implementation at the back end, which initially started out as the Node.js version of the implementation. So this API kind of becomes the sort of heart of your kind of design process and your thinking, and it becomes a kind of boundary between your clients and consumers and implementations. From the consumer perspective, it doesn't make any difference what the implementation is. If it's written in Node.js or Go or serverless functions or COBOL on a mainframe. If it exposes that same REST API, it makes no difference to you as a client. And as a client, of course, there's going to be classic things like the web applications and mobile apps. This is the sort of standard pattern that allows people to easily create both a mobile version and a kind of web app version of their service or of a product, but also, command line interface that people who might want to automate it, or even other services, treating your application or your service as a black box. So the API becomes absolutely crucial, and it's effectively your contract between what you're doing and providing and your clients. So this concept of API as a contract is kind of quite important. And it's all around agreeing the shape of your API. Once you've got that that shape agreed, you can build your implementations that provide that API and implement it, and you can start building clients. So if you are working, in an agile team, or you're splitting this work up, as perhaps you are, you could start working on this straight away. Especially if there's technologies to be able to mock these APIs quite quickly, so you can sort of work in parallel on both sides of this. When you're talking about this shape, we are talking obviously about the operations you're going to be doing in the API, the models themselves, the entities, what fields they have, what properties they have, all of that needs to be taken into consideration. So when we're talking about REST, RESTful APIs, the kind of key way of defining this contract is using Open API, which is previously known as Swagger. So it also gets called Swagger quite a lot. It's now called Open API V2 and V3 have been coming out in the last couple of years. And these also allow you to define your API as a document and use auto-generation. So you can auto-generate the Swagger definition, which itself is a JSON or YAML description of your API, or vice versa. Create this and then use the tools to generate code. If you're not going down the RESTful route, HTTP route, some people are adopting another technology for microservices called gRPC. I won't talk deeply about this today, but that enforces by default you to have a contract. So REST doesn't. REST is going to let a bit of quite free format. There's no sort of standard implementation. For gRPC, you have to define what your API looks like in these protocol definitions. So that's just an example of our Smilr API, all the different operations you can do on events and posting feedback, all the kind of standard kind of create, read, update kind of operations you'd expect. And there's a couple of links there. We'll obviously share the slides at the end for some good practices when it comes to RESTful API design. So when it comes to the actual implementation of Smilr, what did it look like in the end? So there was a bit of a journey here. I've worked with David on this probably for on and off, not every day, for a couple of years now. And it's ended up looking a little bit like this, with the front end being written in a JavaScript framework called Vue.js, and that's a single page application. Most of the work's obviously done on the client, but there still needs to be something to serve that single page app up to the client. So it's a very simple service, basically serving up static HTML content, static content for JavaScript, and any of the entities required for that. That also has a config endpoint. It's a very basic endpoint for the single page application to be able to fetch its configuration at runtime from the back end. So one of the challenges with single page applications is injecting configuration into them. And so creating this API dynamically. The real key heart of the whole project is the data API service. So this is the sort of microservice that provides the data layer. This is what the single page application makes all of its calls to fetch its data back and forth. So it's client side HTTP requests to this service to fetch all of its data. That in itself is communicating directly with a backend data store. This went through several iterations, but we ended up using NoSQL technologies and settling on Mongo. The nice thing about Mongo is we can run it in a number of different ways. We can run it as a container, we can run it as a virtual machine, we can run it in services like Azure Cosmos. And then that has its own kind of wire protocol. So we're not talking HTTP there, we're going to be talking directly. So the data API service kind of wraps the Mongo database. And then some optional components, this being a microservice kind of architecture, we can add in and bolt on extra elements when we need them. So the data API service can optionally call off to like Azure Cognitive Services to get sentiment analysis. So somebody leaves a comment, there's some text in there, we can get the sentiment of that. We don't want to be able to do that kind of number crunching and AI kind of model ourselves. There's off-the-shelf services like Azure Cognitive Services that can provide that to us. So that's basically just another RESTful API that we plug into our application. But it's optional. It's not kind of if it doesn't happen, it's not kind of instrumental to the heart of the app. And this allowed us, to have these implementations of the Smilr API and the app to be able to deploy in different places. So we can deploy it as containers. These are Azure services here: Azure Container Instances, Azure App Service, Azure Kubernetes Service, or in fact any Kubernetes implementation. Once you've got it containerized, effectively the world's your oyster. You can run this in a number of different platforms, and that's really what we wanted to show. So when it comes to security, this was quite a tricky one. We went through a journey here, certainly when this application first started, and we wanted to just show people how to deploy sort of a microservices app like Smilr to Azure. There was no security at all. This wasn't great. So I quickly hacked in some sort of fairly simple one-time password security. It was a little bit better, but still not great. And so I settled on, which is the kind of industry standard way of securing a single page application, is to use what's called the OAuth 2 implicit flow. The challenge here is if you can't store any private information in your single page application because it's all loaded in the client. Simply can go into their browser, view the JavaScript, and they'll see any special keys or any secrets or any passwords you put in there that will basically be available to the client to very quite easily extract out. So this implicit flow does away with that, and it's it's like I said, it's a standard flow, part of the OAuth 2 specification, and it kind of looks like this, where you have a provider, in this case something like Azure Active Directory, which can provide tokens. Well, the user logs in with a login request, gets provided an ID token back. We can use that ID token to go and request an access token. So the access token is for the access of our API, our Smilr data API, and we say we want to be able to access that API. And then we use the token given back to us to call that API. We put it in the headers as an authentication header, and the Smilr API then has to validate that token, because if we don't, then we're just, we haven't secured anything at that point. We still have to reject requests that don't have this token. So we use a method called the JSON Web Token Validation, decode that, and make sure that it's a valid token. And this is a really standard pattern for single-page applications and security. So with that, I'm going to hand back to David to talk a little bit about coding the Smilr. What I talked about, we have different implementations of it. I talked very much about the Node.js implementation, a standard implementation. Let's talk a bit about what it looks like with Orleans.
Right, am I back on then? The screen. Hope so. Right.
Yes.
So yes, let's talk about how we actually took that Smilr model and implemented in Orleans. Now, I love Smilr. Ben and I have consumed many cups of tea and coffee over the years discussing that. You've had a little bit of the history there as to how it came into being. I think it's a fascinating way of facing some of the real challenges about the real world implementation, such as the security we've just been talking about. But for me, what's fascinating is, as Ben said, played around with a number of different databases, different models. At no stage did we not have a database in there. The assumption was there would be a database. So this was an interesting challenge for me and the Orleans project, is can we take something that's sort of entrenched with the idea of a database that holds the core data and move it to an actor-based model. So this is what we ended up with. It's a relatively simple, straightforward implementation. I ripped out all the database stuff and replaced it with grains, and I built it on .NET Core 3.1, which is the long-term supported solution. It's in C#, and I'm currently using Orleans 3.2. It's interesting to note that Orleans is kept very actively in sync with .NET Core as it's gone along, very active in keeping the latest innovation, has piggybacked on that. My model, really simple, starting off with an MVC Web API, because I'm a C# kind of guy. MVC Web Apps, that's where you typically starting point. So I worked on that, and that is the client into the silo. And I built two types of grains, one that represents each of the events that take place. We'll remind ourselves of what that looks like for Smilr. And one for the aggregator. And as you can see on this diagram, my client is on the left-hand side of that line. It's the only thing that's allowed to make calls into the system. The orange represents grains, one per event, and that aggregator grain. Ben has showed you the Swagger definition, the OpenID stuff. So that was my starting point too. If I'm going to play in this game and you become part of the Smilr ecosystem, I need to implement that. So on the right-hand side, handcrafted a load of the implementations needed for both events and feedback in the system. Those are the two kind of key building blocks. And on the left-hand side, very simple, classic MVC Web API code here. I have a post when I create a new event in the backend system, and I grab the body, pull out the title, turn it into an event code. That was one of the design criteria, was to create short event codes inside the system. And then I call getGrain to start talking to the grain that represents that particular event. And remember, of course, grains are virtual. This event will always exist, even if I've never seen it before. So I don't have to worry about if it's a new grain, then do one thing. If it's an existing one, do something else. The system handles that for me. And I just pass in the core data it needs and return back the event code. So really simple, really straightforward. It's useful at this point, as we talk about the grain implementation, is to think, what does that Smilr system look like? As you said, we picked it because it's very easy. Everyone's walked through an airport or something and pressed one of those buttons with a smiley face on. Behind the scenes, to build the system, there's some admin capabilities that requires for each new event, such as a day's workshop, for example, you create that event. That's when we use the terminology an event, and it has a date associated with it and one or more topics. So if it's a workshop for the day, there may be 5 sessions, and what you want to do is create 5 topics and then allow users to feedback on each and every one of those topics. So that smiley button, when you press the happy face, it gets routed to that particular event, to that particular topic, and hangs off that. So that is a perfect fit for the Orleans way of working, because each of these events is autonomous. It has its own internal state, the type of event, the start date, each of the topics, and all the feedback that amasses over the day as people press the happy or unhappy button. Now, it's important that we hold on to this feedback, so we also have to persist the data for this to make sure that, you know, it behaves in a coherent fashion and withstands failures on the underlying system. The starting point, of course, because it's API driven, is to create an interface that defines all the methods. And what's nice here, because of this persistence model I've been talking about, for me as a programmer, making sure that my state gets persisted requires no extra work other than to define a class with all the member variables that need to be persisted and include it as part of the definition at the top of the slide there, and say which persistent storage provider am I going to plug in. Once I've done all of that, Orleans will handle the hydration and rehydration under the covers without me needing to get involved. And all I need to do is, on the left-hand side of this slide, implement these 4 methods to handle all the logic needed for the event. So for example here, when I get an update method to indicate that there's been a change, perhaps a new topic's been added, everything gets passed into me. One of the API calls I can make inside of Grain is to reach out to the current context and find out who I am. So I can reach out and call get primary key string, find out what my key is, because I'm probably going to need that inside my code. And in this case, update that internal Grain state, so the member variables that I've set aside to be persisted. And then the critical bit halfway down this slide, write state async, is when I flag to the system, I want this state persisted as a checkpoint. And from here on in, I am confident now that that system is being put in place and laid into a persistent store so it can be recreated at any future point in time. The final bit is to call the aggregator grain, and this is the grain that's responsible for having a system-wide view of every ID that exists on the system, and it's the one that will take the query. So I need to call into it with the minimal information is that it needs in order to do any queries, such as what events are there on a particular day. So why do we have to do this? And this opens up one of the interesting aspects of picking a framework. Cross-grain querying is not something that's either recommended or really supported. And if you think about it, that makes sense. Imagine a system with tens of thousands of grains, each representing one event. If you want to ask the system how many events took place on the 5th of January, that's a lot of work, and you don't want to be building bottlenecks by querying all the different grains here. So what it requires is a CQRS style approach, where what we need to do is separate the reads from the writes. So what happens is the calls to the grains are used to update the state of the grain and to implement the logic necessary. But if I need to do a cross-grain query, I need to go to another part of the system. Now, the good news is this all gets hidden behind the web API, so the user of the system is totally unaware. This is an architectural decision that sits inside the silo and inside my code. The 2 main approaches that people tend to take in this system are, if it's a read-heavy system that might have the requirements for complex filtering and the like, then what you may be best off doing is exhausting, to push out from the grains a denormalized list with all the data and push it into a store such as SQL or whatever that can be used for the query. So then we end up with one part of the system, the Orleans grains used for updates, and an external data source, denormalized, optimized for queries that you could plug Power BI into or use it to execute complex queries. And that works really, really well. The other approach is to use an aggregator grain, so it's to keep the problem within Orleans and create a grain that can be queried, that knows about all the other grains that are existing in the system. In our case, this makes sense, partly because I just wanted to show off Orleans and show two different grain types, but partly because our query requirements for Ben Smilr is a very simple one. It's a filter in the past, in the future, or a specific date. So that's very easy to implement in code. The model I've gone for is we have one aggregator grain for the entire system. And that's the one we talk about. That was the green one on the previous slide. Now, obviously, in a real world system, that's not a good design. It would very quickly become a bottleneck for updates and queries. And there are mechanisms of having placement of individual grains, one per silo, to balance that out. But to keep this simple, that's not the implementation I've gone for, just to help you get your head around the model. So that aggregator, really, really simple. Implement the four methods it needs to do. One is to check whether an event, and the other one is to add an event, delete an event, and list the events given a query filter that's passed in. And all I have to do inside that aggregator grain is contain a list of all the events along with the minimal details that I will use for querying. Once I've built that, then we have grain-to-grain communications. So as you saw on the previous slide, when I updated an event, what I need to do is call that aggregator and update it. And it's a really simple process. It's a normal grain that just maintains its own internal state. So that's something I wanted to call out, particularly in the session, because of this need to sometimes separate out in a CQR style fashion the reads from the writes, and having a grain-based system with the logic locally means you have to approach querying in a slightly different fashion. So with that, I shall return control back to Ben, and he'll talk about how he took my code and got it up and running in Orleans. So in Kubernetes.
Right. Hopefully everyone can see my screen this time, and I haven't this up. I think I'm sharing this time. So I'm going to talk a little bit about how we took what David did, which was taking the sort of Smilr API and creating an implementation in Orleans. And then we really wanted to see about running that in Kubernetes, because in parallel to this, I've been doing a lot of work in getting Smilr deployed into Kubernetes, or let's say the reference implementation of Smilr, which was the Node.js kind of classic way of doing things. Could we take the same approach from Orleans and get that running in Kubernetes? So just a quick introduction to Kubernetes in case people aren't familiar with it. I should imagine most people will have heard of it at least, because it's pretty hard to escape in the industry at the moment. Kubernetes has become the de facto container orchestrator. It's a way, fundamentally what it comes down to, a lot of people think Kubernetes is a really big complex thing, and it can be in certain cases, but what it boils down to, it's a way of automating and running containerized applications. So, if you have apps that you've containerized and you want to run within Docker, and you want to take that to production, where you want to be able to scale them, run them over, multiple instances, being able to deal with failures, that becomes quite complex, and that's something you can hand over to Kubernetes to run and manage for you. It's a very kind of portable system. You can run it, even on at the edge on IoT devices. You can run it on a Raspberry Pi, or you can run it at sort of hyperscale on, thousands of nodes up in the cloud. It's a very open project, very extensible. There's lots of ways you can hook into this ecosystem. So there's a big community of projects around this. And it's become, very well adopted way of running containers. Some of the common scenarios we see is, lift and shifting to additional workloads. The one most people associate with Kubernetes is microservices, and that's probably what we're going to be exploring a little bit. But there's also the use cases around machine learning, IoT, DevOps. So, Kubernetes is not strongly opinionated on what you use it for. It's a system for you to be able to run almost anything. So when it came to deploying Smilr in Kubernetes, this is the non-Orleans version of it, let's say, the kind of standard version. Way it was stood up, this is a very common pattern. So what you'll see for most kind of single page applications or anything where there's a web component and a backend API, it will look roughly similar to this in Kubernetes. So there's a way of deploying that front end host, that hosts single page application. That's not very heavyweight. We might want to deploy that over a couple of different pods and then expose that out to the internet using a service. That's quite a lightweight component. We don't need that kind of heavily replicated around our cluster. Similarly with the data API, again, it's a stateless component. We can run that across multiple pods in our cluster using what Kubernetes calls a replica set. We can say how many replicas we want, and Kubernetes will just handle that for us. And we put a service in front of it to allow us to be able to access those pods. In this case, the data API is critical, so we perhaps want to scale this out to more pods if we needed to. And then my backend, I decided in this case, for example, to run my database in the cluster. You don't have to do this. The recommendation typically is to run your database out of your cluster and use a kind of cloud service if you can. But in this example, we've got the Mongo database there running in Kubernetes as well. That's running as a single pod, and it has its data stored into what's called Kubernetes calls a persistent volume. To allow access into this, we create what's called an ingress, which is like a layer 7 routing to be able to route traffic to the different services. So this is the kind of almost canonical way of standing up a kind of web application with a database backend in Kubernetes. So what did that look like when we had the Orleans version of the Smilr? So things were slightly different, and certainly for myself as a person that spent quite a long time deploying things to Kubernetes, this was took a little bit of an adjustment. So from the API perspective, David talked about this MVC API, very standard, similar to what we had before. So we have expose that out using the Kubernetes service. That's allowing port 80 traffic in through an Azure load balancer into the cluster and distributing those requests to the pods where we're running that MVC application. It's stateless, so we can just deploy it across as many pods as we want. And then we have the sort of more Orleans specific part, which is the silo. So we deploy the silo in what Kubernetes refers to as a stateful set. And we decided we'll have 2 of these for resilience. So we'll create multiple silos, silo 0, silo 1, and those 2 are running. Now, normally you'd create a service in front of those to be able to allow communication to those pods. The recommendation generally of Kubernetes is not to allow direct traffic to pods. However, Orleans provides a clustering mechanism. It has its own built-in application level clustering. So this is the Orleans runtime here. It lets you provide a number of mechanisms to implement this. The one we went with, which I think is the default, which is using Azure Storage, Azure Tables, as a synchronization point. So with this, the silos register themselves in this table. You see now the entries in the Azure table there for each of those silos, and they register themselves with their IP address. So this is how they keep themselves in sync. They know which silos are alive, and it's also how clients discover how to connect to the Orleans cluster, if you like, this cluster of silos. So they can query this table storage. They both need connections, of course, to the table storage, the standard Azure connection string mechanisms. And from that, they can decide which silos to connect to, which ones are alive, and use the IP address to directly connect to those silos. So this seems kind of obvious, but if you've come from this sort of creating other applications in Kubernetes, this will seem slightly an unusual approach. But it's we're kind of handing the clustering and the failover mechanism to Orleans rather than having to worry about bringing that into Kubernetes. So what did this look like? Appreciate we haven't got time to do a full sort of deep dive on Kubernetes manifests, but I think hopefully this should be fairly easy to follow. So when we deployed the Orleans silo, we used a mechanism called stateful sets. The reason for this is by default, Kubernetes gives random names to your pods. They're semi-random, let's say. And so, as you remember on that table previously, the silos register themselves in this table storage. If we didn't use a stateful set, they'd get a random name and they'd register themselves again and again and again. Using a stateful set guarantees that they have well-ordered names. That's why we've got silo 0, silo 1. So we decided to run these 2 replicas. So that's what the replicas 2 up there requires. We haven't put a service in front of it because we're going to hand over network discovery to the Orleans cluster mechanism. We do have these fairly unusual ports being exposed. These are standard ports used for the Orleans system by the silo. So these ports 30,000 and 5 ones, they're the defaults that we decided to go with. And we needed a way to connect back to this storage account to be able to use the table storage. As this connection string contains a secret or sensitive information, let's say, we used a mechanism in Kubernetes called secrets to store that so that the information is not visible in plain text to anyone looking at the deployments. Oh, and then middle there you can see the image name. So that's where we're storing that image in Azure Container Registry. We've already built that image, pushed it up to the container registry, ready for Kubernetes to be able to pull that down and run that. So you'll see that the reference in there is Smilr Orleans /silo. That's going to pull down the silo image that we built. On the other side, the client, which is the MVC API, we don't use a stateful set. We use what Kubernetes refers to as a deployment because it's stateless. So then it will just spin up a number of pods, give them random names. We don't really need to care about the lifecycle of them quite as much. You see the container image is really similar. It's in the Azure Container Registry, but instead of /silo, it's /API. This also needs the connection string to the same table storage that the cluster's using, so it can just go and discover them. And rather than those silo ports we talked about, it's going to listen on port 4000, which is one of the MVC Kestrel ports. And what we end up doing is exposing this out to the internet using a Kubernetes load balancer. So this then maps between port 80 and the outside world and port 4000 on our pods. So that's quite a sort of traditional, way of deploying a web-based application. To this point, yeah, it is a very standard kind of piece of code. And just lastly, to see this up and running, this was running on my machine last week. So that you can see on the left-hand side, small Orleans API, Orleans silo running. You can see the pods running there with the green dots on them, meaning that they're up and running. And you can see me making a post request across to the endpoint. You see some of the JSON, what it looks like, and the HTTP response coming back. And at the bottom, you can see the logs of the silo there. So I'm actually getting the logs of the silo backend, and you can see the kind of grain events coming in, the event IDs. So this was a kind of live view as it was running inside Kubernetes. And we can see the different parts as it was all hooked up and running inside my demo Kubernetes cluster. So with that, I think we're about done. David, are you still there?
I am indeed, yes. Thank you. Brilliant description of Ben had the Herculean task of taking my code and making it work there. And we went through a big journey discovering that stateful model and how it differs. But all this is all open source. It's all available for you to play with. So you can see links to where you get started, where we have the samples, documentation. It's all out in the open. Please get involved in all of this. And then the specific stuff for Smilr there, Ben has loaded up the slides into his repository, and Smilr, Benco.io, that's where all this code is. So, you know, if this has excited you and you're keen to find out either about Smilr generally and microservices and all the things we've learned building that, or Orleans and want to do something more than a Hello World program, this seems a great place to start. We've both learned a lot in the process, and we've had some great input and support from the product team in Redmond, who we know and who've been very active in giving us feedback and tips and tricks, and the Gitter.io team are very active as well. So we'll leave just a couple of moments in case there's any more questions coming in that we can answer verbally rather than a side panel. Oh, the feedback slide, then we need the react.
Okay. Sorry. Yeah.
No worries. So yes, please just take a few moments to visit this link and give us some feedback. It's important for us to be able to run these sessions like this and know what stuff folk want for future sessions. So please, if you've been listening live, go in and complete this.
Yeah, I think we can I think most of the questions are on the Q&A chat. So,
so
we want to spend a couple of minutes on them, or?
A quick one, yeah. So the slides, we've just put up that link and we'll copy it into the chat meeting. Someone's asked, and is the recording? Yes, it will be up on YouTube, probably typically a couple of days from now. Someone's asked about popular systems used Orleans. There was an early slide in which I mentioned some of the internal Microsoft stuff. So we talked about Halo and how it was used there. So there's a bit more info there, and the paper that's linked to in the slides gives a lot more info on that as well.
Okay.
Brilliant. Well, I think if there are no more questions, thank you for your time, Ben. Thank you very much. Please fill in that survey and keep a lookout for the recorded ones, and visit the Smilr repository and get engaged.
Thanks, everybody.
Thank you.